Good afternoon. This is, as you all know, that this is an important year for IMSC. Two reasons. One, we are celebrating 75 years of India's independence. Basically, the science, mostly science-related things that we achieved in last 75 years, and also 60 years of IMSC actually. So we are. This is the year of 60th anniversary of IMSC, and these two occasions, that we have a series of talks, not only to celebrate this 60 years of IMSC, we also celebrate the achievements of some of our colleagues in the institute. One of them is our colleague, Professor Meena Mahajan. I would like to congratulate on behalf of IMSC that she has received Fellowship of Indian Academy of Sciences 2022 for Mathematical Sciences, and it's indeed a proud moment for all of us. And we'll have more actually in this year from many of our colleagues. This is going to be the first talk in this category, so I welcome Ms. Meena Mahajan to talk about her work to us. And before that, actually, I request Professor Raghavan to introduce her family for those words.
Thank you. It gives me great pleasure to introduce my long-time esteemed colleague, Professor Meena Mahajan. She's a professor in the Theoretical Computer Science group at this institute, which is affiliated to HPNI, as we all know. She joined IMSC in 1994. That's a long time ago. She obtained her bachelor's and master's degrees from the Department of Computer Science and Engineering at IIT Bombay in 1986 and 1988 respectively, and her PhD degree from IIT Madras in 1993. Her research interests encompass many aspects of computational complexity theory, including Boolean function complexity, algebraic circuits, proof complexity, and space-bounded computation, some of which will figure, I guess, somewhat in today's talk. As recreation, she loves solving jigsaw puzzles, creating order out of disorder, and also solving combinatorial puzzles, which crop up in real life situations far oftener than one may think. I don't know whether she means she solves them far oftener than one may think, or they crop up in real life more often. But it's not clear whether she's addicted to them, as some of us might be. Less nerdy interests include reading fiction, enjoying nature, cooking, and spending time with family and friends. Professor Meena.
Thank you very much for the introduction and for the invitation to give a talk here in this series. So today I want to talk about the complexity of formal proofs. And formal proofs, proofs is bread and butter in theoretical computer science, but formal proofs is something that I have been looking at only in the last decade or so, and I want to convey a little bit about what this area is about. So to begin with, what do we mean by a formal proof? So for that, I would like to pose this question: how do we even state a proof? So intuitively, we all have an understanding of what we mean by theorem proof, theorem lemma, proposition proof, and so on. So here's a theorem. There are infinitely many primes. Nobody in this audience is going to doubt that this is a theorem. But if one had to prove it, then there are multiple ways in which one could go around proving this. One, like depending on the audience, you might just say, "Oh, this is elementary, it doesn't need proof." But depending on who you are speaking to, maybe it's not so convincing, so you give a kind of a little bit of a hint. This is how you would be able to formally prove it. And for many people, this would be enough. But if this is not enough, then you could give some more detail and spell out in a little bit more detail how exactly one would go around creating a formal proof out of this. So you can see that the theorem is the same. The theorem does not change, but the proof changes, and it depends on who is giving the proof, to whom you are giving the proof, how it is going to be read. And this is something which is, of course, mathematically not precise. The proof should not depend on context. We talk about mathematics dealing with absolute truth, but we can see that the proof is relative to the context. So why are there so many different proofs? Well, the goal of a proof is to convince the target audience that indeed the statement is correct, and therefore it is natural that the proof will depend on who the audience is. So the claim statement should be is correct. This you want to convince the audience, and well, in many situations, you would also like to convince the audience that you even know why it is correct. I mean, if you imagine a teacher-student interaction, a student assignment which has a complete proof but written in such a way that the teacher suspects the student does not know why it is correct, would not be acceptable. But for now, let's leave aside the second part. Let's focus on the first part. The goal of the proof is to convince the reader or the listener or whoever it is that the proof is indeed correct. So, what would it depend on then? Then the level of detail required would depend on the ability of the person who's reading the proof checker. And what exactly do we mean by ability? Well, many things go into this. Ability would depend on the mathematical maturity of the proofreader, the facts which are already known, what is the known database of knowledge beyond which you can go. So you don't always want to reinvent the wheel. You don't want to always reprove every little lemma that you're using along the way. Ability also crucially depends on this last factor, the time available with the checker. So you could write down a proof of a theorem which is 100 pages long, but if the proof checker does not have time to read that 100 pages, there's a good chance that the proof checker will just say, I don't believe your theorem. It depends on the context. So the resources available with the checker also make a difference. And actually, in this talk, this is the aspect that I really want to focus on. That's why the title, The Complexity of Formal Proofs. Okay, so trying to understand a little bit more these points about ability, it turns out that a lot of modern proof checking is not done by human beings, it's done by computers. Okay? So modern proofs are checked by computer programs. Some of them are even produced by programs. Some proofs are even produced by programs, and whether that is good or whether that's dicey, is this really a proof? That's a different discussion. We're not going there today. There's a lot that can be said about that also. There are fairly long pages on Wikipedia about long mathematical proof, the longest ever mathematical proof, and so on. Some of them will figure in today's talk, but that's not the real focus. So we're not talking about producing proofs. We're rather talking about a proof has been produced by whatever mechanism, and you just want to check and certify that the proof is correct. So now if we look at proofs being checked by programs, and remember we talked about the ability of the proof checker. There's mathematical maturity, there's the database of the proof checker, and the time available with the proof checker. So the proof checker is now a program. And the program could well have been written by a programmer who has immense mathematical maturity, who has a lot of background knowledge, and who has lots and lots of time. It's quite possible. But notwithstanding all that, the program itself, once it is running, once it is given a proof to check, it is going to expect that the proof follows a very rigidly specified syntax and that it follows very clearly stated unambiguous inference rules. If there is any deviation from this, the program is likely to say this proof is wrong or I do not understand this proof. The proof may not be wrong, but the program is not going to pass it if it does not satisfy these two criteria. So that's where formal proofs comes in. So we are talking about theorems, proofs, what is a convincing argument. So it's like quite natural that we have to use the language of logic. What other choice really is there? We have to specify what is the rigid syntax for a proof checking program to work, what are the unambiguous inference rules that could be used. We have to use the language of logic for this. So what do I mean by unambiguous rules? Well, we have seen these kind of statements and combinations and all kinds of IQ tests, logical reasoning, how good, A is to the left of B, B is to the left of C, and C has 3 people ahead of him, or can you conclude something? So here's one very small example. You have statements like this, and instead of writing out these statements each time, I would like to use some shorthand notation, which is again, just symbols to stand for statements. P is the statement that it rains, and this symbol here is the negation symbol. So negation of P is that it does not rain. Now you can already see the difference between logic and natural language. In natural language, negation P could be stated as it does not rain, or it could be stated as it is not true that it rains, or not of it rains. These are all different things, and you can imagine that a program would get confused by such things unless it was exceptionally smart. But using this logical symbolism, variables, negation of P, we have no such problem. So that's one advantage of using such a rigid syntax. Now, here's an example of a rule. From these two facts, if I knew the fact that if it rains, we'll play chess, and if I also know it rains, then it would be reasonable to conclude that we'll play chess. And this is a very well-known rule in logic, modus ponens, which comes, it's a Latin phrase the way of affirming by affirming, so to say. It's saying that if you know P and if you know that P implies Q, then you can conclude Q. But stated this way, now this P, Q here, they could refer to these statements, they could refer to other immensely complicated statements, they could refer to other very simple statements. It's entirely up to us. As long as we have this structure, we know P and we know that P implies Q, we can conclude Q. Now this is a very unambiguous inference rule. How to use this rule is up to us. How we instantiate the variables in this rule is up to us, but this is one example of what I mean by an unambiguous inference rule. Here's another rule. Now, if I know if it rains, we'll play chess. If it does not rain, we'll go cycling. Then it is safe to conclude that I'm going to either play chess or go cycling. One of the two will happen. So the rule here can be stated like this: is the cut rule. If P implies Q and not if P implies R, then I can conclude that Q or R will happen. One of the two will happen. So one can build up many such rules. Now people have studied the expressivity of various such rules. But this was just to give an example of what I mean by unambiguous inference rules. The other question is, what do I mean by rigid syntax? So, if I have statements A and I have a statement negation of A or B, then I can conclude B. But what is the form that A and B can take? So, on the previous slide, the A was the statement P and B was the statement Q. So, they were very simple statements. In general, they need not be simple. A and B can themselves be complicated statements built up from other statements through all kinds of Boolean combinations. One syntax which is used very often is the syntax of clauses. So you can have certain kinds of statements and then you just say that at least one of them must happen. So it's a disjunction or a logical or, P1 or P2 or up to Pk. So it's a simple statement or its negation. Another kind of statement which could be used in such inference systems, even though it sounds more like an arithmetic or an algebraic statement rather than a logical statement, is something which uses linear inequalities. So I'm going to think of these variables x. Each x is either true or false, but instead of thinking of it as true and false, I can say 0 or 1. 0 means false, 1 means true. Or in some settings, even 0 means true and 1 means false. Whatever. I have values for variables, I have meanings, and then I can assert something like this, that the combination of this particular linear combination of the variables is at least t. So the weighted truth of those assertions there is at least t. Seems like a strange thing to do, but there are lots of settings in which these kind of statements are also very useful and one can do reasoning about these statements. Okay, so depending on who's taking the proof, we will set up some kind of syntax, we will specify what are the inference rules that are going to be allowed, and then we will hopefully generate proofs that machines can check. But why are we even bothering about machine checkable proofs? Given all this skepticism, healthy or unhealthy, I don't know, about computer generated proofs. So now we're talking about computer assisted proof checking. Do we really want to go there? I mean, is it a transient phenomenon and we need not bother much about it, or is it here to stay? Well, I really think it is here to stay. I mean, proof checking by computer, it can help in many, many different settings. For one, it can help in discovering proofs. So even though I'm not, like I said, I'm not really going to focus on discovery of proofs, but proof checking and proof discovery very often go hand in hand. It can help in automated reasoning, which is going to be behind all kinds of, which is already behind all kinds of modern day systems. It can help in the verification of systems. It can also help in understanding collapses and separations between computational complexity classes. And that is the reason why I initially got really interested in this field. So as an example of the contrast between proof discovery and proof checking, the planar four-color theorem, which I think virtually everybody here knows of, so I did not spend time drawing a pretty picture about this. If you have a network with vertices and connections, and if it's possible to draw this network on the plane so that the connections do not cross except at their endpoints, then the four-color theorem says that it's possible to color the vertices with just 4 colors and adjacent vertices will not get the same color. And this was a theorem which was proved in 1976. It had been conjectured for a very long time. It's more commonly known as the map coloring theorem. So it was proved in 1976 by Appel and Haken. Their proof, it is completely infeasible for a human being to check. And when the proof first came about, it did lead to a lot of questions about, is this a real proof? Is this real mathematics? Is, whatever. So one of the main reasons why the proof is so hard to check is that it was a computer-assisted, it was not a computer-generated proof, but it was a computer-assisted proof, and computational power was used in a very big way to rule out lots of possibilities. So some years later, simpler proofs also came about, but they also used, they were also computer-assisted. In particular, there's a proof by Robertson, I think, and some others 20 years later. In 2005, there was a proof by Gonthier using a general theorem proving software. I think he used the so-called theorem assistant Coq, and he generated a proof of this theorem. If I wouldn't say that this proof is any easier to check, but what this proof achieves is that it moves the trust requirement from that humongous computer program which was actually checking multiple possibilities, what Appel and Hakim wrote, and tried to check whether indeed everything has been dealt with satisfactorily. So that trust requirement is now moved to this particular software. How is this software working? What does it do in order to add on new inferences to what is already known? And presumably this is an easier task, and therefore you have more faith in the fact that the theorem has been proved. So there is a shift in trust requirement which could happen because of specifying the proof in a certain format. But nonetheless, in this case, the proof was not discovered, was not checked until 2005. It was discovered using this formal using computational power. So the main point I want to make here is that computer-assisted proof discovery and computerized proof checking, they are very different motions, and they're calling for very different skills. So I'm not really here to discuss what is happening in the first part. I'm here to discuss whether this can really make a difference and what is it that we would want to do in this context. So therefore, rather than the four-color theorem, which does not illustrate this point very well, let me move to a different question, the Boolean Pythagorean triples problem, which again many of you may have already heard about. A Pythagorean triple is a triple of numbers, positive integers, which satisfy the Pythagorean relation. A square plus b square is equal to c square. So there are some triples written out there. And Pythagorean triples problem asks, can we partition all the natural numbers into two groups? Let's color these numbers. There are the red numbers and the green numbers. Can we color all the numbers, red and green, such that if I look at only the red set, there is no triple in that set, no Pythagorean triple. If I look at only the green set, there is no Pythagorean triple. So every possible Pythagorean triple has somehow got separated by this coloring into the two different sets. It's a very simple to state problem, and people had looked at it for over 100 years without any idea of how to solve it. It seems a bit strange because the statement involves numbers. It seems like using some kind of combinatorics, some kind of arithmetic, maybe additive combinatorics. Surely there should be a fairly simple proof of this. That didn't seem to be the case. One could also, instead of looking at all natural numbers, consider just bounded sets. So instead of asking, can we break all Pythagorean triples? Can we break all Pythagorean triples up to n? Fix a number m and then ask at least up to n. Well, if you say m is 10, can you break all triples up to 10? Yes, you can. 3, 4, 5 should be separated, 6, 7, 8 should be. It's like easy to see that you can do this. Okay, so for 10 you can separate, for 100 you can separate. How far can you do this? So the question really is, can you separate all triples? And here we are asking a bounded version of it, which makes sense if we are talking about computational requirements. So this problem was finally solved only in 2016, though it was first posed sometime in the 1870 or 1880. It was solved by these three people, all three computer scientists. Like I said, the question itself seems like a mathematics question, but it was solved using computer scientists, and obviously computers played a role in this. And their proof approach was the following. You write the statement that we are trying to prove in a suitably chosen logical language. The language that they chose was that of propositional satisfiability. Use computer-assisted proof search. Now, this is like similar to proof discovery using computers, but there are some differences. Use computer-assisted proof search to either find a proof or to rule out a proof. So you don't know a priori whether the statement is true or false. You somehow try to figure out which of these holds. And you are trying to find a proof in a specific format. Now, this is the point where, which really caught my interest. The format of the proof has been fixed. The syntax, the inference rules, all that has been fixed. In that format, is there a short proof? It could well have been that the statement is perhaps true and there is a proof, but there's no proof in that format. Then this approach is doomed. So this is what they did. They tried to find or to rule out a proof in a specific format, and then they did get a resulting proof, and that resulting proof was huge, but it was in a machine checkable format. And then that proof which was generated was fed into a program checker which could actually check that every point of the proof was, every step of the proof was correct. We'll come back to this a little later. At this point, I just want to say that somehow what has happened here is that, proof discovery and proof checking in this process, they actually went hand in hand. It's not that there was one set of procedures which was used to discover the proof and another set of procedures which was used to check the proof. So discovery and checking This was not the case for the planar four-coloring theorem. There was a proof discovery and then there was the checking. They were completely disjoint. But in this case, for the Pythagorean triples problem, they were really intermeshed. And that is something which is very interesting. We'll come back to this point a little later. A more practical setting that I'd like to talk about is system verification, which I did mention earlier. So in a completely real-world setting, you have these large, maybe industrial plants or some maybe even a medical system with lots of parameters sitting inside, and you want to say that the system always behaves as it is expected to behave. Does the system always behave as expected, always, or on long enough runs, or so? You do not have the luxury of testing it. I mean, especially, if this system is something which is critical, you can't afford a mistake. So you want to abstractly reason out that the system is correct without actually stress testing it in that sense. So what would be done is to formulate the requirements as logical statements, and the system is good if for every run, for every possible way in which the system could evolve depending on what inputs are given to it, the system satisfies all the constraints and meets the expected behavior. The system would be bad if there is even one run on which some constraint is violated. So now the task of proving that the system is good comes down to, once we have the logical formulation, we want to prove that the logical formulation of this, of a statement which looks like this, the system behavior violates some constraint, that formulation should be absolutely unsatisfiable. There's no way you can make that happen. That's what we want. And the proof itself, the proof that indeed this system will never violate a constraint, this statement is unsatisfiable, that proof must be convincing. For somebody who is thinking of actually deploying that system, that person should be convinced that indeed the system is not going to misbehave. So the proof must be convincing, which means presumably that it must be short and it must be checkable. But at this point, you could ask checkable by whom? And the system typically is going to have hundreds, thousands, maybe even millions of parameters. So at this point, you could say that really there is no real alternative to machine checkable proofs. I mean, even if you want to convince somebody that this system is safe to be deployed, that safety convincing can only be done by producing a proof that a machine can check. A human being is not going to be able to check this. So really there is no alternative. This is not a transient phenomenon of producing machine checkable proofs. The final point, the reason why I said that we should bother about such formal proofs, is the connections to computational complexity. And a very quick two-line primer: computational problems. For simplicity, I'm looking at problems which only involve a yes-no answer, not problems which involve computing some values. I pose a question and I want to know is the answer yes or no. Okay? So problems which can be solved efficiently in time, they form the class P, polynomial time. Problems, there's another class of problems, non-deterministic polynomial time. Problems where, well, we don't yet know for many of them whether they can be solved efficiently or no. Maybe they can. But what we do know is that whenever an instance has the answer yes, there is a short proof which can be easily checked. And easily checked presumably by a computer, but maybe even by a human being. Okay? So short witnesses for yes instances, short and easily checkable, easily verifiable proofs. There's an even larger class P space, which is problems which can be solved efficiently in space. They may take a lot of time, but the amount of memory they require is not too large. And there's this landmark result from over 50 years ago by Stephen Cook, who showed that a problem from logic, namely propositional satisfiability, is one of the hardest problems in NP. In fact, so the nomenclature we use is that this is a problem which is NP complete. So this kind of represents the full power of NP. If you can solve this efficiently, then everything in NP can be solved efficiently. So it's the ultimate problem there. And it's talking about, this class NP of problems. It has a hardest problem. Not just one, there are many hardest problems, but this problem satisfiability is one such hardest problem. So it's talking about computational efficiency or non-efficiency. Curiously, the title of the paper is Theorem Proving Procedures. It's not talking about computation directly there. So this interconnection between computation and logical reasoning was always there from many years. So at this point, if you are still with me and if you have been following what has been going on, you should be a little bit suspicious. So how could there even be a connection to computational complexity? Because complexity talks about how does your time requirement grow as your input size grows. I give you larger and larger matrices to multiply, you will take more and more time. I give you larger and larger networks in which to search for a path, you will take more time. So more time depends on the size of the input. But we are talking about proving theorems. A theorem is a single statement, a fixed statement. So where is the concept of growth or computation as related to input size? Well, to bring in this aspect, you have to think of a theorem in terms of classes of theorems. So as an example, this Boolean Pythagoras triples problem which I mentioned, it said can you partition all the natural numbers, but we can look at bounded versions of it. Can you partition the numbers up to n? Can you partition the numbers up to 2n, up to 5n? As m increases, the theorem has changed. Right? It's essentially the same theorem, but something in it has changed. Has the theorem size changed? It looks like you still have just one statement, and in that one statement, one number, okay, maybe you require a few more bits to write a larger number. The size probably has not changed significantly, is what it appears like. But it turns out that when you start writing these things carefully, you write down the constraints that should be satisfied in the logical language that we have chosen, for instance, propositional satisfiability, then this number n plays a much more significant role. The number of clauses that you will generate depends on n. So you have a statement which has many different variables, many different clauses, and then you want to ask whether it satisfies some constraints. So now you can ask this question: how does the proof size grow as the theorem size grows? Well, I shouldn't, at this point, theorem should still be in quotes because it's a theorem which you're trying to prove, a potential theorem. As the size of the statement grows, how does the proof size grow? So in 1979, Steve Cook and his student Robert Recau, they laid the foundations of this area, propositional proof complexity. Basically, if you look at problems in NP, yes instances have short and easily verifiable proofs. No instances, we don't know whether they have short proofs. Is there a short proof of the fact that the answer to this question is no? That is not known. So NP is kind of lopsided class. Yes instances have short proofs, no instances don't. So if there is no short proof for these no instances, then we would be able to conclude that NP is not equal to the class of complementary problems. And therefore, that would also imply that P is not equal to NP, the holy grail in computational complexity. So, therefore, to separate NP from co-NP, it would be enough to show that for some problem in NP, no instances do not have short proofs. Short proofs in what format? At this point, we have to ask this question. We cannot evade that question forever. So, we will need to show that there is no short proof in any easily checkable format. Now, asking that there is no short proof in any format seems to be a rather tall order. So, if we step back and look at the computational question, if is P not equal to NP, then we want to say, is the satisfiability problem hard for any algorithm? There's no algorithm which can solve it fast. But it is enough to look at only satisfiability. You don't have to look at all problems in NP. So, once you pull out one complete problem, that captures the class and you can just focus on that. So, similarly, it is very natural to ask, is there one representative format? In this format for the proofs, if there is no short proof, then there is no short proof. That would be the proof size analog for NP completeness or whatever. It turns out that in this setting, we do not know the answer. We do not yet know whether there is so here we don't use the word complete because complete in logic means something completely different. We use the word optimal. Is there an optimal proof format? Is there an optimal proof system? We don't know. And therefore, we are stuck with, it seems to be harder to prove this statement, that there is no short proof in any format. What we can do, since we do not know how to approach this question, is to try and show that there is no short proof in specific formats. Pick a particular format which you know how to reason about and deal with, show that there is no short proof here. Then try to make the format a little bit more general, add more inference rules perhaps, and say, okay, there is still no short proof. Try to gradually build up so that eventually we have enough understanding that in no format is there a short proof. So if we fix specific formats, then there are many such lower bounds which have been shown. And these lower bounds, even though they are looking at specific formats, they are quite valuable because in practice, systems are using these formats. So then, even though these results don't say that you will not have any short proof at all, they are saying that your systems will not find those proofs because they are using these formats where the statements are hard. Another big question in this area, so there was one question about optimality of proof systems. Another very big question is, how hard is it to find proofs, assuming that those proofs do exist? So, if potential proofs are very long, then an automated proof search will take too long, of course. If you know there is a proof 100 bits long, then you may potentially have to search through all settings of those 100 bits to find the correct proof. So, lower bounds on proof size will say that they will expose inherent limitations of proof search methods. But if the proof size is very large, if you can show that the proof size is exponential, the proof search method is likely to be doubly exponential. So, that's terrible. Even when there are short proofs, you may not be able to find them. even if there are short proofs, finding one could simply be too slow because the search problem is exponential in the checking of it. In general, searching can be harder than verifying, and it's very similar to this question of PNP. So one could ask this question: for which interesting proof systems does this thing hold that whenever there are short proofs, we are able to efficiently find them? So this is the question of which proof formats or which proof systems are automatable. And for some systems, we know that they are definitely not automatable. For some, we know that they are somewhat automatable. And there's a lot of stuff which is still out there open. We do not know enough about it. So let me come to this specific format, one specific format. So propositional proof systems are what Steve Cook was talking about in the 70s. So in these proof, so I've been interchangingly, at some point I moved from formats to systems. It's really the same thing. A proof system is a format for writing a proof in which you specify how to write the theorem and what inference rules you can use. So the format of the theorems in this setting are tautologies, propositional tautology. So a tautology is a statement which is always true. This tautology has all kinds of variables in it. So there's x1, x2 to xn, they are Boolean value variables. Each variable takes a value true or false. And these variables are connected using logical Boolean connectivity, logical or, logical and, logical negation. So you connect these variables using these things and then you get some humongous expression. Like if it rains, then this happens and so on. Those are the kind of statements. And it's a tautology if no matter what true false values the variables take, the overall expression remains true. Individual variables may sometimes be true, sometimes false, but the overall expression is always true. And what we really want to know is whether a statement is a tautology. A simple example of a tautology is this: x or not x. It doesn't matter what value x takes. This or is always true because one of x and negation of x will be true. A more non-trivial example is something like this. I'm not even sure whether it's very clearly visible, so maybe I will skip past it. It's an expression which uses variables and negations and some logical ors and logical ands, and it has quite a few clauses. Depending on the value of n, it has some 2n clauses. And if you think through it a little bit, it turns out that no matter what values you give to these x and y variables, some disjunct somewhere is satisfied. You cannot make everything simultaneously false. So this is also a tautology. So how do you prove that a statement is a tautology? The statement is given as some Boolean expression involving Boolean variables. There are some free variables. They are connected using Boolean operations. And you want to know, is this a tautology? Is it possible to falsify it at all? Well, we can follow this set of equivalences. F is a tautology if for every x, fx is true. There is no x for which fx is false. There is no x for which negation of fx is true, which means that this negation of fx is something which is unsatisfiable. So this brings us back to the satisfiability question. So we can focus on deciding whether a propositional formula is satisfiable or is it not satisfiable. And that will tell us how to answer things about tautologies. So this satisfiability, of course, is the NP-complete problem. It's likely to be computationally hard. Despite the fact that it is computationally hard, SAT solvers have been enormously successful. Today in real-world applications, SAT solvers, which are programs which try to decide whether a propositional formula is satisfiable, they seem to do very well. So it seems to be a contradiction in terms until one realizes that these solvers are being used in specific applications. So in those applications, whatever formulas are generated, they inherit some structure from the application. And the solvers are able to exploit that structure. So the solvers will not always work well on arbitrary formulas, but for formulas arising from specific applications, they are doing pretty well. And they can decide expressions which are quite large. They run into thousands, sometimes even millions of variables. They are able to decide satisfiability. So the way these solvers run, at the end of the run, if the given formula is not a tautology, then typically the solver gives you an assignment. When it stops, it says, look, here is this assignment on which that expression is false. That's why I'm saying that f is not a tautology. So it gives you the witness. Okay? So that will be a proof that f is not a tautology. When f is a tautology, the solver stops at the end and says, yes, f is a tautology. It has to give some proof. One possible way of thinking of a proof is to say what are the steps that the algorithm took along the way, and those steps constitute a proof of some kind. It's a proof in the programmer's head perhaps, but from that proof, from the solver algorithm, one can actually extract a proof format, which is a proof format of the type that we were looking for. Unambiguous inference rules, which are used by the algorithm along the way, a completely rigid syntax which the solver program was using in making its steps. So underlying every solver algorithm, there is a formal proof system, and it is those proof systems that we would like to talk about. So going back to this Boolean Pythagoras triple problem, I said that there was this connection between proof discovery and proof checking, and at this point I can tell you a little bit more about this connection. So what these three people did was they denoted this statement Sm, that triples up to m can be partitioned. They tried to express that as some kind of a logical statement in propositional satisfiability by giving each number a variable. Variable is true means it's a red, the number is colored red. Variable is false, it's colored green. So the statement is there exists a coloring of the numbers for which there is no triple of one color. No triple of one color is extremely easy to encode. For every triple ABC, you're just saying that at least one of them must be red, at least one of them must be green. So at least one of those three variables must be true, at least one variable must be false. So if I want to take this statement Sm and write it logically, I'm just saying that there are m Boolean variables, one for each number. And for every Pythagorean triple in that set, there are two clauses. Each clause has only three variables in it. I just write out this formula, which is not too large. And I ask you, can you satisfy this formula? If you can satisfy it, you have found the partition. If you can't satisfy it, there is no partition. So we use a solver. And solvers are limited by how much time they have available to them. So they had to make their solvers more and more efficient to push how large an m they could deal with. At this point, you should also realize that they are taking a calculated risk. They must have presumably suspected the answer is no. Because if the answer is yes, you can keep on increasing m larger than that, and you will still keep finding partitions. At what point will you be able to say that yes, I can always find partitions? Whereas if the answer is no, there will be some finite point at which you will stop and say at this point I can no longer find the partition. And that is exactly what happened in their case. They went up to 7,824 and their solver kept finding partitions. At 7,825, it did not find a partition. It spat out a proof that there is no such partition. But the process of reaching 7,825 was not trivial. They had to keep tinkering with the solver algorithm to make it more and more efficient. And remember, every time you touch that algorithm and change what inference it is allowed to use, you are changing the underlying proof system. You are allowing it to use a stronger or a different inference rule. So the proof format is changing. So the proof format was evolving until it reached a stage where the computational power they had was enough and they were able to get this. So finally, we know that the Boolean Pythagorean triples problem, the statement is false. You cannot partition all numbers. You cannot even partition all the numbers up to here. So if you go up to here, there are 7,825 variables. There were these many triples, 9,400. So there were 19,000 clauses. By modern SAT solver standards, it's not that large. But nonetheless, their solver ran for 30,000 hours on a fairly powerful computer. And the solver is loosely based on some kind of, a proof system resolution. And it spat out, as I said, a proof in the format DRAT, which is currently the most commonly used format. The proof length was 200 terabytes. So this was only in 2016, and in Nature there was an article which started 200 terabyte math proof is the largest ever, and the caption says, "No, is this really math?" So exactly the same question that was asked about the planar four-color theorem was asked here too. This is a very nice picture from there which tells you the colors. Some numbers have to be assigned these colors. They use red and blue, not red and green. And the whites there are the numbers for which it doesn't matter what color you use. They don't kill any triple in any way. So anyway, so the point there was that for solving this question, they had to simultaneously tweak their proof format and the way the proof could be checked and the proof discovery. So it was a proof discovered using computers, but the proof checking went hand in hand with the discovery. And like I said, the underlying proof system was a fairly complicated thing. It was not just resolution, but it was loosely based on resolution. So this resolution proof system is a very simple proof system. It simply says that it's a system which underlies most current widely used SAT solvers. It simply, so this is the format that it uses. You have an AND, a logical AND of various clauses. Each clause is a disjunction of some variables or their negations. And there is just one inference rule. The inference rule says if I already know that A or X is true and I already know that B or not X is true, then I can conclude that A or B is true. Something which right in the beginning with that cycling or playing chess, I said this is the cut rule. So it's something which is very easy to, it's very appealing to see that this the statement indeed, this rule is valid. Just using this rule from a bunch of clauses, you eventually try to derive, you infer more and more clauses. Finally, you infer the empty clause, which has no literals. There is no way you can satisfy an empty clause. No? To satisfy a clause, you have to make something in it true. And if there is nothing in it, you cannot make it true. So, if you can start with a bunch of clauses and using this inference rule, you can derive the empty clause, then your formula was unsatisfiable. That's all resolution does. So you can see that from the nature of this proof system, it's going to be extremely easy to check proofs in this format. And the checking process is so elementary that you can parcel it out to computers, you can parcel it out to multiple human beings, each one of which is just checking that each application of the inference rule is valid. So proof checking has been distilled down to something very, very simple, but massive. Many steps to be checked, but you don't need to worry about individually what those steps are saying. It's a very syntactic check. And here's an example of a proof using resolution, but I think I'm going to skip it now, and I'll be happy to discuss this a little later. This is because let's not get into such notation. What is it that resolution can do? Well, formulas which state something like this, if you have some directed graph with edges going in a certain direction, and I have constraints which say that at the sources everything must be true, and I have constraints which say that if these two things feeding in here are true, then here also it should be true. Separately, I have another constraint saying at the end it must be false. This is not satisfiable. You cannot assign values to all the nodes in the network. Resolution will be able to very easily prove that this is not satisfiable. So typically the formula size, when you write this out in our logical language as clauses, as conventions of clauses, the formula size will grow linearly with the graph. The proof size will also grow linearly. It won't be very big. But on the other hand, here is another formula, the pigeonhole principle, which to us is completely obvious. If you have n plus 1 pigeons, you want to cram them into n holes, they will be crowded. Each pigeon cannot get a hole to himself or herself. Here, if I try to write this as a formula in the syntax that we chose as a conjunction of clauses, then the number of clauses will be roughly n cubed. N plus 1 pigeons, n holes, roughly n cubed clauses. So the size of the formula will be n cubed. But we have a proof that to try and show this is unsatisfiable using resolution, we will require exponential in n steps. So a solver which is based on resolution trying to discover that, hey, here there is a bottleneck, is not going to discover it efficiently. It seems a bit bizarre. A statement which is so obvious to all of us is so hard for this proof system, resolution. Should we even bother? Does this mean that this proof system is too elementary? Well, the proof system is simple, but that's not the real problem. The problem is that this principle, pigeonhole principle, stated this way, it is obvious to us. But when we are trying to verify a real world system and we have written out all the constraints in our logical language, hidden inside that may be an invocation of pigeonhole principle, and we may not recognize that it is pigeonhole principle. Like I said, verifying the safety of a system may involve millions of variables. There are constraints all over the place about this variable. If this is 1, then that is 0, this is 1, and so on. When you chain it all together, somewhere a pigeonhole principle is being violated. You don't notice it because you are not looking at million variables at one shot. You are feeding it to a program. That program may not notice it. And if it does not notice it, it could well go down this rabbit hole trying to prove satisfiability and end up spending an exponential amount of time. So at least this lower bound tells us that we should guard for such situations, and if there is a possibility that this is appearing in our system, we should be able to deal with it separately, not directly feed it to the solver which is trying to check our system. There are other formulas which are also very obviously false, but resolution struggles with. Anyway, let's keep that aside. In the last few minutes, let me just tell you a little bit about what happens beyond SAT, and that is really the area that I have been working on. So resolution-based SAT solving has been immensely successful. So it was like very heartening for a lot of people that even though the satisfiability problem is NP complete, we can work with it. We can use it in real world situations. So therefore, why should we just try to solve satisfiability? Maybe real world situations with even more complex logical formulations we are able to solve. We might be able to solve. So let's develop more complex formulas. And one way in which this could be done is by adding complexity in terms of mixing these quantifiers. So a tautology says for every assignment to the x's, something happens. I could say for every assignment or there exists an assignment. So here's a simple example. If I say there exists a value to the x's, x1, x2 to xn, and there such that no matter how I set y, the inner product is even. This is a true statement. I mean, I just set x to 0, then for every y, xy is even. But if I change this around, there exists x for every y, xy is odd, then this is false. Because if you set y to 0, then you're always getting a value 0. So now I change the x to universal, the y universal, or for every y to existential, and I put in a statement like this. Well, this statement is true. You can see, even if you don't follow exactly what is happening there, The fact that I'm mixing these two kinds of statements, for every possible value of x something happens, is one flavor of a statement. There exists at least one value of x for which something nice happens. That's a different flavor. And now I'm mixing these two. That makes things enormously complicated. So this logical language is not more expressive than propositional tautology. It's the same things that you can say, but you can say them much more succinctly using much shorter formulas, shorter theorems. And that then brings us to some very interesting happenings. So one way of understanding this jump is that NP typically talks about one player games and whether it is possible to win those games. Is there a way to solve to satisfy all the constraints in the Sudoku setup? It's a one player game. P-space, polynomial space, which is, as I said, is a much larger class. It's talking about two player games, and a canonical example of that is Antakshari. You set up some kind of game. I want to ask whether the first player can win. Is there a way in which the first player can move so that no matter how the second player responds, there is a way for the first player to respond, no matter how. So there exists for all, going back and forth. And that is why you need these so-called quantified Boolean formulas. So the variables are quantified, either exists or for all. They are not all of the same type. It completely changes the complexity of the game. And in this setting, asking which formulas are hard to refute, which are easy to refute, requires a very different kind of thinking. So this QBF proof complexity is an area I was introduced to this around a decade ago by my friend and collaborator Olaf. Some of you have seen him because he does visit IMSC quite often, not in the last 2 years, unfortunately. So what we, I think maybe I should skip this. Yeah. So quantified Boolean formulas look like this. You have initially a quantification prefix, there exists for all and so on, and then you have some formula inside, and then you want to ask, is this formula true? And this can be explained by a two-player game. I said P-space captures two-player games. Two-player games can also be used to evaluate QBFs. Okay? So QBF is true if exactly when the first player the existential player has a way to win. I have an example here which I think I should skip completely and go back. Oops. Yeah. So to prove that QBFs are false, as I said, we do need we need to go well beyond things like resolution and all, which work for satisfiability. We need new ideas because the variables are behaving differently. And so the moment you have mixed quantifiers, resolution is fine, it's not enough. We need to add augment these systems in different ways. There are ways of augmenting them. They are very clever, some of them. The question one would ask is, why are these good proof formats? Why are these proof systems? So to show that they are proof systems, you would need to show that they are complete, which means that for every false QBF, there is indeed a proof in that format that it is false. If you cannot refute the proof in that format, then the format is somehow weak. No, it is not able to do everything. But usually this is easy. You take the QBF, you convert it to a game. In the game, somebody has a winning strategy and you use that winning strategy in your proof. Usually, although not always, this is the easy part. There's also a soundness part. You should be able to show that if at all there is a proof in this system that this formula is false, then the formula had better be false. You should not produce a fake proof of falseness of a formula when the formula is actually true. And this is usually much harder, and it often involves extracting from an alleged proof a winning strategy, which then certifies that yes, that formula is false. It requires much more subtle constructions here. So the work that we have been doing here is to get a finer understanding of which lower bound speaks. Okay, now I'm not even moving. It's not me. I have to take more slides. Hold on. Yeah. So in our work, what we have been looking at is trying to get a finer understanding of, we know something for propositional satisfiability. What from there can be transported to the QBF world? The QBF world is much bigger. What is it that we can transfer? What is it that we cannot transfer? Where do we need to augment and do something very different? So a very good understanding of this. This is ongoing work in many different settings, which we have been doing. We have been comparing the relative strengths of different proof formats. Here I'm talking about formats for QBF proofs, not for satisfiability proofs. And we have also done some work proposing new QBF proof formats, new QBF proof systems, and exploring their relative strengths and limits. So this is something that I've been working on for the last 7-8 years with Gaurav, who is a student here now, Anil, who was a former student, and these are my collaborators across the world, Germany, in England, in Austria now. I think. Yeah. In particular, there was one QBF proof system that we introduced 3-4 years ago, and then after that, Gaurav has been working quite a bit on it. It's a new format for proof. So this was not an existing format which we tried to understand better. We proposed the format. In this format, we tried to put in the winning strategies in that game directly into the proof format. So this required some subtlety. Why should a proof about a strategy player? But we were what inference rules are allowed and what are not allowed, that obviously matters. So all of these contribute to how complex a proof is. Proof complexity itself is aiming to understand what are the strengths and what are the limitations of various solvers. So by solvers, I mean a generic class of algorithms which tries to decide whether a certain formula is true or whether it is false. So proof complexity is aiming to understand the limitations of these solvers, and then by giving lower bounds on the sizes of proofs, it also more optimistically, I think, aims to separate or collapse complexity classes. I don't think that a collapse is going to come through a proof complexity approach, but one never knows. Yeah. SAT solvers are useful even in proving mathematical theorems, as I mentioned with the Boolean Pythagorean triple problem. Propositional proof systems are explaining the underpinnings behind those theorems, and QBF solvers are the next stage. SAT solvers have already achieved a lot. With QBF solvers, we could hopefully do a lot more. We could probably, they are likely to be much more useful in practical settings where we are looking at verification, and maybe they could be very useful for proving newer theorems, for discovering theorems. So the underlying theoretical underpinnings of QBF solvers, QBF is QBF proof complexity. This is a relatively younger field. It's taking off now, and that is the area in which I'm currently obsessed with. So, thank you for your attention. I'm happy to take questions.
Questions?
Hi, Meena, a great talk. I missed the first 5 minutes, so I don't know whether you already covered it, but this reminded me of the Russell-Whitehead program to convert all of mathematics into kind of logic. And my understanding was that, like Gödel's proofs in 1930s essentially demolished that whole enterprise. But now that you're mentioning, like people are using SAT solvers, it kind of seems that that dream is back in place. Like whether you can essentially convert all of mathematics into propositions whose truth can be checked. So can we, in some sense, say that the Russell-Whitehead program is back online?
I'm not sure I would put it that way. So there is, so I think what you're talking about is also like this connection between recursive function theory and computational complexity. So we are really talking about computationally bounded problems, and that makes a huge difference. So Gödel's theorem, like you said, killed that program by saying that it is impossible to have a system which is sound and complete, which can prove all theorems. But I'm not aiming to prove all theorems. I'm aiming to only prove theorems of a particular type, corresponding to the class co-NP or corresponding to the class P space. It's possible. But the question of whether there are optimal proof systems or not is perhaps related to that, and maybe that will be an explanation for why this is a question which is still open. We do have, computationally, we have complete problems, but we do not, for proof checking, we do not have optimal proof systems yet. But we do not also have a proof that there are no optimal proof systems. So I think I would not say that this is bringing back that dream. This is a very much resource bounded version, but of a similar flavor.
Could you give us an example of a mathematical or a combinatorial problem that has a particularly concise and interesting QBF formulation?
So Antakshari, that's not the kind of, so you want a mathematics statement?
Conceivably, there could be some elegant.
So let me formulate Antakshari as a mathematical question, but it could also come out of your Facebook connection graphs, for example. So what I mean by Antakshari is that I'm giving you this huge network. There are lots and lots of vertices, and there are connections, but these connections are now directed. And there are two players. Player 1 starts at a particular vertex, and then player 2 can choose any node which from which this node has a directed edge. So imagine that there is a token on this network. The token starts at a particular point. Player 1 makes a move and slides along an outgoing edge. Player 2 makes a move, slides along another outgoing edge. The only rule is that you cannot go back to a node which has already been visited. So once a token has ever been on a place, there is a stain on that spot. You cannot go back there, right? So who dies out first and has no place to move to? So if I think of this as a computational problem, the input is going to be a network and a starting position. And the computational question that I ask is it the case that the player who starts, who makes the first move, has a strategy to win, no matter how the other player wins? This can be very concisely stated as a QBF. So as it turns out, QBF is something that can express everything which can be done in polynomial space. So there are like all kinds of things that one could encode that way. But what I'm not sure what I should be explaining at this point, which will convey the encoding directly.
Great talk. I had one as a follow-up to Sitapra's question. So you actually had a statement somewhere saying that maybe this statement is true, but it is not provable within this proof format that you're using. That sounds very much like Gödel's theorem that you have in any axiomatic system there are things, and one way is to expand your proof format, but there will still be things that you can't prove. So is it that different from?
So in general that could happen, but since here we have the luxury that we are dealing with these computationally bounded problems, proof formats which are not complete, where there are formulas which cannot be proved in this format, we typically discard them or we augment them until they become complete. So even here towards the end, I briefly mentioned why these QBF proof systems are proof systems. So we expect that they are complete and they are sound. So they are sound, meaning they don't end up proving something which is false, but they are complete. They can prove everything which is true, which is stated in that format. So in the process of devising newer proof systems, one could at intermediate points step up, you see a shortcoming of a proof system, but there's a particular kind of formula which seems to be very hard to prove here. So maybe I need to add an inference rule, or I need to change the way a particular rule is being used. That may destroy soundness. So then you add some more rules, and then at some point it may even become incomplete. Then you continue tinkering with it. You don't call it a proof system until it is sound and complete for the class that you are considering. So this is something that we do not compromise on.
Another question, if I may. So this in discussing this resolution, you mentioned that it does very badly in the pigeonhole principle exponential time. So what if you augment the axioms that it works on with the pigeonhole principle with, or in general, can you just manually prove certain things that are useful and add them to the computer proof system? Does that help?
Yes, you can, and it does help, and modern day solvers do this. So there are these SAT SMT solvers, satisfiability modulo theories. So certain statements are given, and then with those you can like short circuit parts of the proof and jump ahead. There are certain what are called semantic implications, which if you detect them, then you can directly use them. The challenge would of course be to detect them in practice, but in theory, yes, once you have detected them, you use them and go ahead. And SAT SMT solvers are being used a lot in practice now, especially in the verification applications.
Last question. What does it mean for, you said the SAT solvers do very well in practice, though it doesn't be a complete problem. When they fail, do they prove something that is false, or do they just take forever to do it?
They take a very long time. They don't give wrong answers. As far as, I mean, I have not heard of instances like this. There are these various competitions and challenges and so on. So they all seem to be correct because they also produce they produce checkable proofs. So at the end, they not only give an answer, they give a proof of why their answer is correct, and that proof can be fed to another checker. So there's a second stage where the trust requirement moves from the proof itself to the checker.
So this is regarding the computational complex classes of in-player games that you mentioned. So you mentioned that one-player game is like the computational complexity is like NP, and for two-player it's like P space. So I remember Conway's classification of these games in his book Winning Ways. He also had a class called no-player games, and he mentioned Game of Life as one such example. So I understand that for life, you can actually make various statements, but all of which can be, you can find easy proofs.
So what is the term that you use?
No player.
No player. Okay.
So there are no players there.
It's just evolution of a system.
Exactly.
Yes.
So would you say that any statements by then, if you try to create formal proofs of that will belong to which computational
The game of life is computationally universal.
Yes.
So therefore, there will be things in that which are undecidable. And then they would fit into Gödel's framework. So there would not be proofs of all such statements there.
Any other questions? If not, let's thank Meena.